be robust when the quantum computers will be in reality. So when the quantum computers will be in reality, that part is actually defined by this post-quantum era, when the quantum computers are physically available with us with the enormous power of the computation, and the code-based recover the intended uh, information as much as possible with maximum reliability. So there are some techniques which are called the coding techniques, especially error control coding techniques. So somehow we are trying to linking this code-based error control coding with the crypto for the security. So crypto is the last word. Crypto is related to the security in any communication, any transactions, and the first word code-based, it is related with the reliability of the channel. And somehow it has been observed that these coding techniques, error control coding techniques, can be exploited as a security system, especially when the quantum computers will be in reality. So let me first briefly describe the idea of the encryption. So if you see, there are mainly two types of encryption model are available. One is symmetric key or private key crypto system. In suppose B is intended to send some information to A, and in between E is some eavesdropper who is trying to tap the information. So this is the idea, basically a very generic model of any security systems. So how will send your information? You have to use some secret key, and you have to encrypt that one such that the other person, means not intended user like E, should not decode it, and the same key is available with the A, so that A can decode it only. So this scheme is known as the symmetric key or the private key crypto system. It is in this case actually you have to share the secret key with your intended user. So that is another cost involves there. Example, advanced encryption systems are there, AES. Okay, another philosophy is there, which is called asymmetric or public key crypto system, where once B is trying to send some message to the A, so one public key B will use for encryption. Public key means it is publicly available with all. Available with all. Okay. So one public key, suppose N, is available with all. So he will encrypt with that one. But this encryption is such a way it will be done that the decryption can happen only with the private key. So private key is the P and Q, suppose I'm telling. So these type of algorithms are very popular in most of the applications where sharing the secret key is a big issue. So for example, this N and P and Q. So our topic, so today's topic will concentrate the security purpose of these asymmetric or public key crypto systems. So the P and Q, for example, I can say, suppose I have N is a very big number which can be factorized in P and Q to prime factor P and Q. So the hardness of the problem is, means complexity of the problem involves that why E will not be able to break it. Suppose E has the very big number. Suppose you can imagine 1,000 digit or more than that big number, which can be factorized in two prime factors P and Q. And it is very time consuming and computational intensive for E to get P and Q from N, because he or she has to try with for example, a brute force or any intelligent algorithm, whatever. But obviously, the issue is that it is possible, it is defined, it is deterministic. Okay, so means if I can give a n which can be factorized with p and q, it may be time consuming or computational intensive, but it is not like that it cannot be happen or it is probabilistic. It will happen with definite results, but it may take huge time. For example, this RSA algorithm for today's 128-bit RSA algorithm, it is taking more than 100 years to break if you apply brute force algorithm. So within that 100 years, you need a transaction over a few minutes maximum, right? So that way, today's crypto systems or security systems are robust in that sense. Okay, the time and computational time required and the computational facility required, that is not available to break it within a due time. Okay, but what will happen in when the quantum computers will be there? So it has been already proved by source algorithm. All of you, I think, already familiar with the source algorithm. So this, we call this an integer factorization. Okay, and other problems are there also, like discrete log problems, similar type of problems in the discrete log domain. So these two factorization problems are usually exploited in today's public key crypto systems. Okay, but source algorithm and with the help of the quantum computers, it is already proven that these things n equal to pq, this factorization can be solved within the order of polynomial time. It can be solved. Okay, and but still it is fine that we don't have enough I mean physically with large number of qubits, quantum computers still far from the reality, but anyhow it will come one day. So in that case, we can assume that once it can be solved within a polynomial time, so once the quantum computer will be there, so this classical, now onwards I will tell those techniques of the public key crypto systems, PKC, like RSA, ECC, all those things. These are classical crypto systems, means these are useful when the classical computer is there. But quantum computers can break it. There is no way to protect. And another point I have just told, this n equal to p into q, this will happen. It may take more time, more computations, but this is a deterministic algorithm. By exploiting that deterministic algorithm, we are giving, as we have a constraint on our resource and time, so we are using the today's security systems. So the 2 points should be clear from here, that classical, these algorithms will be breakable by the quantum computers with the source algorithm and searching algorithm like Brower's algorithm. And these classical algorithms, the reason why they are breakable, because these algorithms are deterministic in nature. Okay, so the idea people found here, that if we can identify any algorithms which are non-deterministic, there may be a chance that with those algorithms we can exploit in the quantum era also. Okay, so that's the idea actually exploited in the post-quantum security systems. So basically the characteristics of the post-quantum secure PKC system should be, it should be random in nature and it should be hard problem. So basically in the algorithmic term, we can say it is non-deterministic polynomial time hard problem. So NP hard problem, those should be. And should not be breakable by polynomial attacks even in the quantum computers. But this is not enough. It is, if still I can propose an algorithm which is not easily implementable, because ultimately those algorithms will be from, if you see from the implementation point of view, this should be maybe implemented in so many portable devices, or it should be a lightweight or something, where the efficient implementation is another constraint. There are so many algorithms in nature which are very hard problems, but similarly hard to implement. So the third important point we have to remember, like efficiently implementable problem should be there. So by keeping in those 3 points in mind, people have tried to find algorithms, existing algorithms in the field already existing, like the coding theory. So the first point, one very, I mean, research is going on this area, like code-based crypto systems. Okay, it is basically the hardness of the decoding of a random code. Okay, so, and our tutorial will be basically focusing on this area. There are some other problems like in lattice. So like the closest vector problem in the lattice, that is also a very NP-hard problem. In hash-based systems also something like solution of the multivariate quadratic equations, there is also the NP-hard problems exist in isogeny. So out of these major 5 things, these are the major 5 areas where people have already found naturally NP-hard problems are there, which can be exploited for the post-quantum security systems. So our aim is for today's discussion is this code-based crypto systems. So now I'll brief about you the basic idea of the code, means error control codes. So before that, let me show you one picture here. So this is the basic block diagram of a error control code. So a source is generated message bit M is the message. It is encoded by some technique. It is encoding. It is not encryption. It is encoding. Okay. So still we are in the coding, not in the encryption or security part. So M bits are there, and then it is encoded in the vector C. So M code with length k bits. Then I have encoded it with C in the C vector, which is n bits, and obviously n is greater than k. So basically I'm adding some extra bits here. So extra bits I am adding, which I call basically n equal to k plus p. So this p is called actually the parity bits. Parity bits. Okay. So idea is that if my message of k bits is somehow corrupted, and these parity bits, p parity bits, these are generated from a message bit. Okay. So the idea is that if I miss something out of this my k message bit, as I have generated my parity bits from the message bit, so I can recover the data, some part of the data, may not be fully, but at least some level of the data I can recover from the parity bits, because they are keeping information of the message bits. Fine. For example, I can say, suppose if k equal to 3, so I have message bits m, maybe my m may be m2, m1, m0, and my code word, or if I say my n k equal to 3 and n equal to 5, so I can say, for example, C is my code word, which is basically C4, C3, C2, C1, C0, which is basically nothing but the M2, M1, M0, and P1, P0. But these two bits actually are the parity bits. And they may be generated with some linear operation between any combination of the message bit. Like, for example, if I tell P0, P1 is generated by XORing M2 with M0, and P0 is generated with XORing between M1 and M2. So you can see this P0 and P1, they are depending on M0, M1, M2, correct? So that means they are keeping some information of this P0, P1, sorry, M0, M1, M2, the message bits. So if somehow my message bits is out, any of these M1, M2, M0 are corrupted, I can recover those bits. There is a chance, at least there is a chance to recover those bits from the those parity bits. So in the other angle also, I can say my message bits are independent because I don't have any control over the message bits, right? Message may be anything from the source. So my message bits M0, M2, M1, I can say these are the independent basis vector of my code space. But P0, P1, those are the depending on this M1, M2, or M0. So that's why I have drawn one picture here, one coordinate system by taking k equal to 3, where my basis vectors are basically M0, M1, and M2. So this is my vector space, and my code word will be a subspace of this vector space. So whatever the code word I can get, they will be placed in this vector space. They will not depend on the P0, P1, because P0, P1 are not basis vectors. They are depending on the M0 and M2. So the task of this scheme is that I will get a message bit of k bit, message of k bits. It will be encoded in a code word C with n bits. And then once I will transmit this one over the channel, there is an error in the channel. So the error will corrupt my code word. That means what I have sent actually, that will not be received at the receiver, right? That will not be received at the receiver. So decoder will receive some vector R, which is basically corrupted by the error. Now the task of the decoder will be reconstruct the code word C by received word from the received word R. So this is the ultimate task. Okay. Now, if I so I think I don't know how much background you have there, but this is the basic idea of the error control codes in a very nutshell I have tried to explain. Is there any question? Okay. So I'm defining my code is this way. So a linear code C, why linear we are telling? We'll tell at the end. So a linear code which is basically error control code, is defined with the 3 tuple with this n, k, and d mean, where n is the length of the code word, k is the length of the message, as I told, n is the length of the code word, n is greater than k always. And this message length is called the dimension of the code, because I have explained, I can, if I want to plot this code word vector in a k dimensional in a vector space, so I need only a k dimensional vector space. Okay, so I don't need n dimensional vector space because I have only k independent basis vectors. And then d mean is called the minimum Hamming distance between any two code words. So if I give another example, it will be good. Suppose I get this k, I got m2, m1, m0. So how many combinations I can get? How many different type of message vectors I can get if I am using in bit? My base is 2, means binary in bits. I have 2 to the power 3 different, total 8 different message vectors, correct? Vectors. So from all 0 to all 1. So each one with this combination will generate some parity bits, and that will be appended with the actual message bits like this way, and will make this code word, right? M2, M1, M0, and then the generated message bit P1, P0. And this combination of the message bits to form the parity bits can also be expressed in terms of a matrix operation. Like if I take M is my message vectors, and I can multiply with the matrix G. So if it is a 1 by k matrix, I have to multiply it with k by n matrix. So I will get a vector C with 1 by n dimension. So this is the equation. Actually, mathematically, I can explain what is happening in the coding. So I have this G vector, G matrix, which is basically called the generator matrix. Means in this generator matrix, how the message bits will be combined to make the code word, especially the parity bits, is defined. The way I have defined, for example, here, XORing M2, M0, and XORing M1, M2 to form P1 and P0 respectively. Correct. So this generator matrix is nothing but defining that combination, how the message bits will be combined to generate the parity bits. And in the minimum Hamming distance, if I say any two vectors, suppose 1, 0, 0, 1 is one vector 1, and another vector, if I say 0, 1, 1, 0. So it has a Hamming weight. I can say the number of ones in the vector, which is 2. This is also Hamming weight 2. But if I want to find the distance between these two vectors in the vector space, so basically the distance maybe in different way we can find, like Hamming distance, other Euclidean distance. So Hamming distance, you all know, is the number of bits in differ between two vectors. So basically the Hamming distance, I can say, between these two vectors is d mean, d Hamming. If I say Hamming distance is 4, correct? So now in this way, as I have total 2 to the power k code words. So as my dimension is k, I have total 2 to the power k code words. Sorry, 2 to the power k message bits. I have total 2 to the power k message vectors, different message vector, right? Message vector. Similarly, there will be one-to-one mapping between the message and the code word. So I will get similarly 2 to the power k different code words. So these code words, among all the code words, if you find this code word, basically code word vectors, you can say. So between all possible code words, if you find this Hamming distance, so which will be the minimum, that is called the minimum Hamming distance. So distance between any two code words in the code book, I can say. And T is the error correcting capability of the code. So as I told, this generation of the this parity bits will help us to retrieve back the original message, but there is a limit. You can't do arbitrarily any error with arbitrarily any code. You can't do. Each code, they have a limit to recover. So that recovery limit is called the error correcting capability of the code. So I am not going in details of those things. So there is some kind of bounds of this linear block code, which is the D mean should be one is the error correcting capability. It depends on the how each of the code words are distance between the minimum Hamming distance between any two code words. Okay, and this D mean also depends your number of bits you have chosen for the code word length and the message vector length. Okay, so that is called last one is called the singleton bound, because D mean is always will be restricted by this N and K, and the error correcting capability T will be limited by this minimum Hamming distance. So to understand this concept, if we go through this figure, so suppose I have this blue circle is my place position of my actual code words, like C1, C2, C3, these are the code words. And this black circle actually the received word, which is affected by the error. So basically I can say R is basically my code word plus error. Now R has also the dimension of K, so that's it will be also a point in this vector space. So I can assume a sphere around the R. Around the R, I can consider a sphere, k-dimensional sphere, obviously. And now my aim will be how this R, I have to recover my decoder. Decoder will try to recover C from the received order R. So there should be so many cases. R may be mapped to C1 or C2. How I will decide? In this case, each code word, around the code word, we are hypothetically drawing a k-dimensional sphere whose radius is the T. T means by this bound, the T is the radius around the code word up to what the code word can correct any error. Means if anything, any received word resides inside the sphere of any code word, so the decoding algorithm should be such a way designed that it will decode to the respective circle code word. Okay, so that means R should be decoded here. But if I received a R here, which is outside, this is my suppose another R dash. So if it is here, then if you see why the R will be previously the black circle, why the R will be decoded as C1, because R resides inside the sphere of C1. But in this case, R dot, it is actually resides outside the both C1 and C2. Then what will happen? So it may happen that they have the similar distance from these two circles. Then where it should be mapped. So these are the cases where our code, whatever the code you design, in every cases this may happen. In some, it may not be able to recover the received data. Means will not be able to decode it properly. Means will not be able to reconstruct the code word from the received word. So that means arbitrarily any error a code is not capable to correct. Fine. So there is a limit always. So if my error is too much, that R resides outside of any of the code word, then I can't do. Another case may happen. Suppose the R was actually related to the C1, but due to the huge error, the R came here inside the circle of the C2. Okay, inside the circle of the C2. The same R, due to the huge error, though it was actual code word was related to the C1, but due to the huge error, it came inside the circle of C2. Then automatically our decoding algorithm will not be able to understand. So it will see, okay, R double dot is resides within the C2 circle. So it will be decoded R double 2 as the C2. So that means this is two cases may happen in decoding. Either if it is decoding properly fine, if it is unable to decode, there may be two cases. Either it will never be able to decode or it will decode wrongly. So that's why obviously as much as large the T means the radius of the circle will happen, if you can design a code, so obviously that will be better code. Similarly, the code words C1 and C2 should not overlap. Okay, so it will never, if your code never be constructed like this way. There should not be any overlap, because if this is overlapping, then if any code word falls inside this overlapping region, so we will not be able to decode it properly. So that's why T is as large as possible. That is good, and each code word should be separated as much as possible. Okay, that's why it is called the distance between two code words. So that's why that is the term D mean. Okay, so D mean is a very important parameter which is actually defining the error correcting capability of a code. So this is the brief idea of the coding. Now see, any question from here? Okay, fine. Now, as I have discussed, so the general encoding and decoding of a linear block code is defined in this way mathematically. So a given matrix, we call that is general matrix G, which is actually encoding, means this way mapping the M into C with this equation C equal to M into G. Okay, and dimension of M is K, and the length of the M is K, and the length of the C is N, but the dimension of the code is K. Now there is a the general decoding algorithm, which is called the syndrome decoding algorithm. Okay, another term I forgot to explain. Similarly, the generator matrix that is called the parity check matrix. Means after encoding at the receiver, basically what you are getting a code word, received code word with received code word with this message part and this parity part, right? This parity part, that actually we are getting. So the job of the decoder will be to check the parity bits to recover the actual code word. So the term is called the parity check matrix. So another matrix is used for decoding, which is called the H matrix, which is a dimension of n by k by n, and it is required for the decoding. And that's why it is called in general, it is called the syndrome decoding of linear block codes. Means I have a generator matrix G. If I have a generator matrix G, the relation between the generator matrix and the parity check matrix is G into H transpose equal to 0. So they are linked. This G and H are linked. If you have G, you know H. If you have H, you know G. So the parity check matrix is given, and you have received a code word, received a word, which from where you have to recover the code word, actual code word. So R is the received word. So this R will be multiplied with the H transpose, which is called the syndrome. So basically you have to find the E of weight T. Means if the weight of the error is greater than T, so you will not be able to decode properly. So that's why we are limiting the error weight T, because my code is able to decode up to T errors. As I told, there is not like any errors it will be able to decode. There's a limit to decode. So I am limiting that weight of the error. So if you see, so this is the equation will remain, because I have R, I have H. So R means R into HT. Basically, R is nothing but the mg, and E plus E. Then HT, if you multiply H transpose, it will be mg H transpose plus E into H transpose. So that way I am getting EH transpose is my syndrome. Okay. So means if there is error, if there is some error which is able to be corrected, so there will get a syndrome. Okay. So that way the syndrome will be this way. So this is the basic decoding. If there is no error, that means syndrome will be 0. So if we get S equal to, so S, whatever the R we have received and whatever the H we know, if we multiply these two things, these two vectors and matrix, so we'll get S. If S is 0, we can say there is no error. Means syndrome 0 means no error. If some non-zero S is there, that means there is some error. Now you have to recover this E, because now after multiplying you get S. So basically now you have this S equal to E into H transpose. So basically you know now S, you know H, you know S. So from there you can find E. So once you are able to find E, you can subtract from the R, and that way you can get the actual code word, because C is. So now if you subtract E from the R, you will get mg. This mg is nothing but the C. So you are getting your code word. So this is happening in the decoding and encoding. Okay. Now this is the basic idea of the error control code, encoding and decoding I have explained. Now how it can be used, or why it will be used in post-quantum scenario. Well, the reason is, as I told, the post-quantum characteristics, these slides So NP hard problem. So non-deterministic polynomial time algorithm you have to find out. In this encoding and decoding, if you see, if I can make it random, so that means G is, you have to know G or you have to know H, right? These two things are very, very important to know to encoding and decoding, correct? Fine. Now, if someone can hide this G or someone can hide this H such a way that it looks random to the eavesdropper, then to the eavesdropper, it will become a random code. And in that sense, for the eavesdropper to decode it or to break it, you need to the eavesdropper, it will looks like a NP hard problem. Okay, let me come there more specifically. So that hard problems here actually two. One is actually the general decoding problem. So I have a code C with gender matrix G and partition matrix H. So the general decoding or code word finding problem asks to find the message M ask to find the message M given the error affected code word R and the gender matrix G. Means mathematically, if you show I have a given G and given R, any unknown error with weight T, from there to find the M, is a hard if we can hide the G. Similarly, in the computation syndrome decoding problem, I can see, so performing the decoding of a received word R of a random linear code, basically finding the error affecting code word is called the computation syndrome decoding problem. And here, given G and you got S, now find the E of T such that S equal to ET. If I hide the H, you'll never be able to find it. Means actual H if I hide. So these two problems actually are already proven in 70s NP hard problem by McElish and other researchers. From there, in 78, McElish actually exploited these two hard problems as the component of encryption and decryption in a PKC systems. So McElish and Niederreiter, then later on in 80s, Niederreiter proposed another system which is actually exploiting the decoding syndrome decoding problem, and the general decoding or code word finding problem is exploited as a PKC system in the McElish system. Now I'll briefly describe these two things. So the definition of G, S, and the G is already told. Now in the McElish system, what the way they are doing, he is doing. So I am defining three matrices. G is my gender matrix, S is some binary non-singular matrix, and P is some permutation matrix. All are from the GF2. Elements of the matrix are GF2 for sake of simplicity. I mean yellow field 2. So McElish used actually some specific code here, which is called the GOPPA code, because GOPPA code construction is much more complex. So the G is complex. So idea of the security. Now I'm coming to the security point. In case of reliability, my aim should be how much reliably I can recover the message. But in case of security, how much complex I can do the thing so that people other people will not be able to decrypt except the intended user. So that's why GOPA code has been taken, because GOPA code generator matrix is a very complex matrix. I mean, looks like a completely random matrix itself. So that's why GOPA code has been chosen. But for in practice, for the error control people, means for the reliability purpose, GOPA code basically is not used much, because the problem with this complex generator matrix, because the aim of the reliability is not to make the thing complex, but the aim of the security is always make the thing complex. And so what he is doing here, as we explained, the private key and public key idea. So the crypto system actually used this way. So this G is the actual generator matrix of the code. Now this G is multiplied by S and P in the front and the end. This S and G are some another random matrix, and the size of those are really large, like in terms of thousands or 10,000s size. And then he is making a G prime. So this G prime actually publicly, now we have seen in case of the normal PKC system, N equal to P into Q, right? N is the public. So similarly, he is doing G prime is the public, but keeping the private actual G and this random S and P matrix, those foundation matrix, these two things, these three things, he is keeping in private. Now the similar concept of basically, if you can see, it is a matrix factorization kind of thing, but ultimately it is to the eavesdropper, he is getting only the G. So this B to A, it is encrypted with G prime, and it can be decoded by A as A knows G, S and P, but to the eavesdropper, he or she knows only G prime. But G prime is not the actual generator matrix of the code. Correct. So the encryption is done this way. C equal to, as a code word, it is sending that C equal to M. The message is encrypted with the G prime, and the error is also added. So this error is a binary error with the some by the weight, limited by the weight T, means how much my code will be able to correct. Code means the G, code related with the G, not the G prime. Now during the decryption, only A will be able to decrypt, because once the C is basically this one, then if I have received this C at the A, means the intended user, I have P matrix. So it is an invertible matrix P. Okay. And then I can multiply the C with the P inverse. So I can get AM, ASG. Then again, is computed with the equivalent to, like, I am just renaming C prime, M prime, and the E prime. So then using the some general decoding algorithm, like the syndrome decoding. So now I have this equation with me, where my G is known to only, the actual G is only known to the A. So I have this G, I have some C prime, I have some M prime, I have some E prime. So I can use the decoding algorithm, and I can get the M prime out of this one. Decoding algorithm means like syndrome decoding algorithm, any general decoding algorithm. Specifically, syndrome decoding algorithm is a basic idea of the decoding, but actually in practice, some much more faster algorithms are used. But the basic concept is same. And now, once I get the M prime by the method of decoding of the linear block code, I can find my M using by multiplying the M prime with the S inverse, because A is known, knows all those P, S, and G. But as this S, G, and P are not known to the E, he will never be able to decode it. So the idea is that to the eavesdropper, this decoding problem is becoming NP hard as the G looks like a geometry matrix of a random code. So if you don't know the G of the code, it will looks like a random to you. So it will automatically become a NP hard problem for the E. So that's the idea has been exploited in this Macaulay system.
Sir, I have a question.
Yes.
Suppose there are like B wants to send message to two parties like A1 and A2.
Mm-hmm.
And
both the A1 and A2 should have to be with G, S, and P.
Okay.
But the idea is that G prime is publicly known.
Yes.
And you will not be recover your G if you don't know the S, P, and G separately. So, and then what is happening with the others, it looks like a random code. Means if you want to decode a random code, which is already proven as the NP hard problem, means it is a random problem. So basically non-deterministic polynomial time problem. So whatever the computation facility you have, it doesn't matter. You may have huge quantum computers with all the facilities, all the algorithms. Till the date, there is no quantum algorithms has been devised which can solve this one. So in that sense, it is a proven, obviously up to the current technology and available resource, it is a post-quantum secure techniques.
So both A1 and A2 should have G and
G, S, and P, obviously.
Okay. Then can A2 act as a can interrupt between the.
Acha, you are telling A2 may be a eavesdropper, right?
Eavesdropper.
Then obviously, but that's the assumption we have to assume. Okay, eavesdropper does not have the access to S and P. He publicly known only G prime. So similar thing can be exploited in other way by the hiding the age, which is actually proposed by the another. These two methodologies are available in whole code-based crypto systems. Post-quantum crypto systems are based on these two things, two problems, as I discussed, like this general decoding problem and the computation syndrome decoding problem. And this first one is exploited what I explained in the Macaulay. The second one, computation syndrome decoding, is exploited in the needed data system, where actually you are hiding similar way age. Similar way you are hiding age. Just I need not to explain it again, but if you have the interest, you can see here in the needed data system, the private key is my age, M, and P. Okay, and ultimately you are publicly availing the H prime, which is basically the multiplication of M, H, and P, obviously with the error bound T. And then similarly, you can, if you go to the decryption part, you'll see if you don't know the M, P, and H separately, though you have available with the H prime, you will not be able to decode the syndrome. So that's why that things are there. Okay, up to this one fine, but still there are some techniques available to break those systems, which is called the most robust techniques is called information set decoding. And these information set decoding algorithms are also probabilistic in nature, and they are basically designing the whole error. They are assuming that error in the first part of the code word or the last part of the code word or the middle part, or somehow it is distributed some according to some distributions over the in length of the code word. So by assuming those kind of things, they are actually trying. Okay. And in some advanced information decoding algorithm are also available. That is, I am not covering here, but they are somehow are applied, and we have tested it, but still their time is actually exponentially increasing. Means if we can increase the size of those matrices, so though whatever the still available intelligent information decoding algorithm available in the market, in the research community, still if we increase the size of the matrices, those G and H matrix, means the code word size, if we increase, so still they are exponential in time. So that's the and that way the research is going on. Now I will just conclude this session with the NIST standardization process. So
Dr.
there
Bera,
are,
sorry to
yes,
interrupt. I think we have exceeded the time, so can you conclude it fast?
yes,
Yeah,
yes. I'll conclude within the next 2-3 minutes.
yeah, thank you.
Yeah, okay, ma'am. So the NIST is National Standard Organization in US. So they are actually standardizing these all security systems. So there is a timeline. If you see, from the April 15th, it has started. So from the April 15th, several rounds up to till date, or total 4 rounds of the standardization process already over. So, and they have asked for submission from the across the community. People have submitted several techniques, proposed several techniques for this post-quantum security systems, not only based on the code based, lattice, multivariate has everything, all whatever I have discussed. And this by this November, December 2020, the fourth round was completed. And for the signature part, the encryption part, mostly standardized. But signature part, the last call was ended by this May 23, and hopefully we'll be able to get the draft version of the standard post-quantum security system by 24. And if you see the submission graph, so initially around 82 submissions were there. Okay, the round zero, what I call the initial. So this blue is showing the signature, and the pink is showing the public encryption system, means encryption system. So there is another part which is called the signature, digital signature, what you call. So this signature is also exploiting the same public crypto system mechanism, but in some different form. Uh, so initially 82 different submissions were there. So at the end of the third round, basically 15 were selected. And if you see the out of the type of how many types applied in the initial submission, code-based techniques, as we have identified these 5 techniques. So code-based techniques was around 24 submission were there, and but the highest submission was from the lattice, and others also there. So the reason we are concentrating on the code-based crypto, because it is a very high chance to stay. And similarly with the lattice. So in the initial submission, this was the statistics, and then at the end of the third round, so around 7 from the lattice based, including signature and encryption both, and from the 3 from the code based sustained. And so this is the things is one of the why the thrust on the code based are there. And there are some other evaluation criteria they have set in the NIST, so not going in details. And few names of the third round finalist in the encryption part, like this way lattice based code. In the code based, actually this classic NACL is what we have discussed. Actually, this is actually the finalist. It went to the fourth round and it has been selected in the fourth round also, code based. And or some alternative like HQC, and the bike is also there. This bike is based on the code. Maculus is based on GOPA code. Similarly, this bike is based on the MDPC code, like medium density parity check code. And this HQC are based on BCH and RS code kind of thing, RMRS code. And in the third round, some signature scheme is there, but if you see, there is no code-based signature scheme selected. The reason is that designing code-based signature scheme still is under question mark. Means still people have whatever the suggestion received, they has been somehow broken with the people by the other community. So this is another chance where people can do their much more research. So that's it. So I am thankful to my, I should acknowledge my group. So our project team consists of three PhD students and faculty with me, and Dr. Bhaskar বিশ্বাস also. And we have two projects running. One is by SAC DRDO New Delhi and another is by QIQT DRDO Bangalore. So we are thankful to them also. Okay, so this is some references. I have already shared this PPT with the organizer. So fine. Okay. Thank you for. So any question, please, if you have.
Yeah, if there are no further questions, then I will thank Dr. Bera for his interesting talk on post-quantum crypto systems. It is very interesting to know this because personally I was not aware of these things, and it is very nice to see what all people are doing in this area. Expecting that the quantum systems will start working, and if they start breaking codes, then how do you make the original codes safeguard the original ones?
Yeah,
so
actually that is another issue. There is another stream of research is there where people are designing the quantum cryptography,
right,
but
right.
and quantum information. But this is the things we are getting naturally intractable problems
Right.
for the quantum era. That way people are selecting. We are
Yeah.
not going basically we are not doing any such research like you people in the quantum domain practically. So we are finding some problems, existing problems, which may be useful for
Yes,
this
yes.
thing.
Yeah, but this is a very interesting line of thought, to take the original things and see where there can be problems because of some new things coming up and trying to safeguard them. So thank you very
Yes.
much for this interesting talk. And
Excuse me,
yeah,
I have a small
yes,
doubt, sir.
yes, please
So
go ahead.
here in your talk, you defined all these matrices belongs to space F2. So why is it so they all belong?
No, the reason is it is for sake of simplicity we have taken as, but there are some codes which are actually maybe the extension field also. Okay, basically HQC. If you see HQC, the example I told, that is actually taking the codes in the extension field of GFQ, means GFQ to the power n or something, Q to the power m. Okay.
Okay.
This is not restricted. Okay, only
Sure.
GF2 should be the case, but for sake of simplicity, for understanding, we have used GF2.
Okay.
But code may be from extension field also, and that is actually may be useful for much more robustness. Obviously, you are correct.
Okay. Thank you, sir.
Okay, so I once again thank all the speakers in the morning session for the interesting talks they have given. And personally, I thank the organizers for giving me this opportunity to chair this session and be part of this interesting thing. So I think with this, we end the morning session. So the admin, is there any announcements you want to make, or we'll just regroup in the afternoon?
Yeah, there are no further announcement. You can just end the session.
Yeah. Okay. Thank you then. Thank you. Yeah. So we